So this last topic is God, it seems like science fiction still. We're going to talk about antimatter, the like evil twin doppelgangers. There's the electron, and there's it's like bad with a mustache positron. The exact same like thing, except it seems to have the opposite charge. And the discovery seems to be that if matter and antimatter happen to collide with each other, it releases energy. Now, I'm not a cosmologist like Stephen Hawking is. I can't pretend to understand all this stuff. Like I think I've said this before. I can memorize and regurgitate information, but I don't really get this stuff. So please don't feel like you have to totally understand it, because like this is strange. This is weird stuff. Um, Anyways, the theory that a lot of scientists, if they study like the origins of the world, I think the term is cosmologist. They believe that the Big Bang occurred because there was a whole bunch of matter and antimatter all of a sudden released. And what ended up happening is the matter and the antimatter collided with each other and released a huge swath of energy, because that's what happens according to Einstein's formula, E equals mc squared. Except there just happened to be a little bit more matter than antimatter, and that's the stuff that the extra matter that was left over is what ends up creating our universe. And so this next topic kind of delves into so many strange sorts of things that we don't even talk about. Ideas about like, well, how did the universe grow? There's a theory about things called dark energy. I don't even fully understand what the concept of that is, but there's just this idea that there's energy that we can't detect or notice or see, and that energy is fueling the expansion of our universe. So, anyways, today's topic, antimatter and quarks. I've got a huge story to read off the first slide, and I'll do what I hate doing, but I can't add anything more to it, so I'll just read. 1894, Charles Wilson builds a device called a cloud chamber. And the goal of this was to put some shadows similar to the cloud tops that you can see, like shadows that you'd see on cloud tops of mountain climbers. So, anyways, he supersaturates the air inside his device with water vapor, and in doing this, he passes charged particles through the cloud chamber, and they were ionized, causing some of the water vapor to condense. And eventually, he was able to track the motion of his charged particle, looking for vapor trails. And I don't fully get this, but this was the thing that resonated most with me. It's similar to how you can see an airplane in the sky based on its water vapor trail behind it. You guys know what I'm talking about when you see that? We were playing soccer yesterday. Kinsey had soccer, and like a bunch of the little kids that airplane, right? Because you can see the tail behind it, right? You can't see the airplane itself; it's too far away. So, from what I gather, shoot charged particles through clouds, and you're able to kind of see the residue afterwards. So, anyways, these cloud chambers were then operated with a magnetic field, so that you could start seeing these charged particles spin. You guys remember how an EMR, a charged particle in a magnetic field, would work according to your hand rules? So, anyways, the direction of the spiral pattern would figure out whether it's positive or negative. So they observed the spiral and they found the charge to mass ratio, and it seemed to be the charge to mass ratio was of an electron. However, that made sense, but the spin was wrong. The spin behaved according to a right-hand rule, which meant that it was positive. Essentially, what ended up happening is Charles Wilson discovered a particle that seemed to have the same charge to mass ratio that an electron had, yet it was positive. What did he discover? The positron. Yeah, that's what he seemingly discovered back in 1984. Right, so that's what I have on the next slide here. Scientists had discovered proof of what we think are the antimatter particles. So that was a positron, which is the anti-electron, the opposite doppelganger of an electron. Well, this basically further again destroys and blows a big hole into our concept of matter. Um, Back in the particle model that John Dalton came up with, one of John Dalton's main points was that an atom was indivisible. You guys remember talking about that point? That's actually where the word atom came from, is atomos, some sort of Greek word, meant you cannot break it into pieces. He was wrong. We discovered he was wrong because, well, hang on, let's have you guys do this. Who discovered that an atom was indivisible, or wasn't indivisible? Who do we attribute that to? Who'd you say? Yeah, Thomson. Yeah, J.J. Thomson discovered the corpuscles, or however you say those, his cathode rays must have been smaller than hydrogen, right? Anyways, well, if we believe that electrons, protons, and neutrons are as small as it gets, actually that doesn't seem to be true either. It seems like you may actually have smaller particles than those. And so evidence of antimatter suggests there's even more going on at the subatomic level, and maybe even the subatomic level. The idea of, well, what gets smaller than that? So I snapped this out of something. I mean, the main things you guys have heard about are electrons, protons, and neutrons, right? And we often use E, P, and N as a way to illustrate them, but apparently there are positrons, antiprotons, so basically an electron that's the size of a proton. I cannot for the life of me figure out, like intuitively, what an anti-neutron would be. Because a neutron's already neutral, so what makes it an anti-neutron? But, well, apparently. And then we briefly mentioned these concepts. Neutrinos and antineutrinos are even smaller still than electrons. Those are like the subatomic particles. So here's what I don't know this. I can remember information and tell you it. Here's what I do understand or can tell you is that the idea is that when matter and the antimatter collide, the term that I bolded here, it's particle antiparticle annihilation occurs, and energy is created. So between the antimatter and actual matter, it would then create energy, which is kind of like a mass energy equivalency. So in theory, then I guess you could be asked a question to figure out how much energy would occur when, say, like a proton and an antiproton collide, right? Well, all you'd have to do then is find the mass of a proton. It's in your data booklet. Find the mass of an antiproton. Say mass, just different charge, right? And then do basically 1.67 times 10 to the minus 27 times by 2 for the two of them, and then times that by the speed of light squared. That would be how much energy is released, right? So it's a pretty easy question. You just have to find the mass of whatever particle we're talking about here. The three of them are in your data booklet. Times them by each other, times it by the second one, right? And then speed of light squared. Okay, so going forward, physicists then asked a natural question like I've been hinting at. Well, what is stuff made out of, right? If I keep breaking it down smaller, what's an electron made of? What's a proton made of? And one of the things scientists started doing is they started using higher and higher energies to try to investigate the structure of matter. And I'm going to fast forward to a picture. It's actually on the next slide. They started creating what are called particle accelerators. You guys ever heard of these? Particle accelerators. I was reading a really fascinating article over the weekend. It was in the National Post. It was talking about um, in space, scientists who are studying outer space, they discovered that there's a cold spot in outer space, and there's a couple of scientists who theorize that this cold spot is because there are two parallel universes crashing into each other somewhere way out there in outer space, and that's why it's abnormally cold there compared to everywhere else. So strange theories. Like I don't even know how you prove it. I was reading another one talking about how when this first super collider came up. You guys ever heard of the CERN super collider? It's in Geneva, Switzerland. Big Bang Theory's talked about it a few times before. They were worried that the very first time that they turned it on, that they would create a black hole that would suck up all the matter in Earth and possibly destroy it. Like, because they had no idea what they were doing at the first time. Right? Because literally what these things do, you can see this big figure eight sort of pattern, right? They end up using charged magnetic fields to accelerate a charged particle in like a circular pattern so fast that eventually they're going to crash them into each other, right? No, I don't know the exact details, but I kind of imagine that what you might end up doing is in this one right here, you just speed it up in a circle over and over and over again, right? Do the same thing on this one right here, speed it up over and over and over again, right? And once they're finally going about as fast as you can possibly get them, then you maybe open some sort of door in the middle of these two things here, and then let them actually crash into each other. And I mean, if you send a proton smashing into another proton, basically traveling the speed of light, maybe you can break it into smaller pieces. You know what I'm saying here? That's what physicists decided to start doing. And so, yeah, apparently some physicists, they weren't sure whether this would actually create a black hole. Wouldn't that be crazy? All of a sudden, Switzerland is just covered in a black hole. I mean, again, there's some theories about how black holes work, but I don't even know that we can prove them, right? Because, well, anyways, you watch The Flash, right? Anybody else watch the TV show The Flash, where he like goes around and circles around the circular thing? I kind of think the same concept. Anyways, I'm gonna go back a slide here. As physicists are discovering these things, someone coined the term the subatomic zoo. Because as they were crashing these particles into each other and trying to figure out what stuff is made up of, they discovered a lot of different things. This slide I found somewhere on the internet there. There are up quarks and charm quarks and top quarks, and Don't even ask me. I'm well beyond my pay grade. But I found this slide here that I think kind of helps narrow it down. And you guys have a chart in your data booklet that lists some of these like subatomic particles. You guys have your formula sheets nearby? I'm pretty sure it starts off by listing protons, neutrons, and electrons. Does it start with those ones? And then kind of go into like up quarks or down quarks. I'm going to come stand by someone who's got one nearby. What do we got here? Okay, so you got electrons and positrons, neutrinos, quarks. Okay, so you guys can see how it kind of lists some of the main particles, like the smallest ones there. Here's kind of a flow chart I found online that kind of lists some of them. And you guys only have just a few, because I've got another one on here that lists so many more. But apparently there's all the fundamental particles. And then there's leptons and hadrons. And then hadrons can be broken up into mesons and baryons. And don't worry about memorizing this because you don't need to know it. But this is kind of how like they've broken things up. And if you care to know even more, this table right here, again, I wrote on here, do not memorize this thing. Don't worry about it. Okay. But like here are some of the small particles. So electrons are very small, smaller than protons and neutrons, right? Electron neutrinos, and then a whole bunch of, I think they just made up these words, like muons, tauons, pions, chions. Like I feel like I'm in Star Trek, because like these just seem like made up words. But essentially, these are like the subatomic particles. So if you would know anything, maybe know the difference between maybe hadrons and leptrons. So hadrons would be consisting of things like, say, the protons and neutrons. And then leptons are even smaller than those still. You can actually tell how small they are based on the mass. Okay. Now, I've got a slide that talks about it a bit later, but why don't I talk about this right now? Rather than measuring mass in kilograms, these things are so incredibly tiny that doing mass in kilograms makes no sense. So what they've done is they've taken the formula E equals mc squared, and they've rearranged mass to get it as energy over the speed of light squared. And then we talked previous day about how a different energy unit would be not to use joules, but to use the electron volt unit instead. And so as a very, very small way of measuring mass, they use a mega electron volt, which is a joule, divided by the speed of light, and that gets them a different unit of mass. And these are so incredibly tiny. Look at this. The proton and the neutron are regular sized things that we've talked about before. That'd be like in the 900 sort of region here. Now, some of these other sort of hadrons here, apparently like an upsilon and a psi are actually bigger than a proton and a neutron. Again, don't ask me. Like, I know nothing more than what I'm telling you right now, right? But like, look at these guys right here. The difference then between a hadron and a lepton, though, is like these guys are really, really small. That makes sense? Long story short, this is like the stuff that the smallest stuff is made out of. And they keep trying to figure out what it's smaller. So. Oh, okay. So this is what I was just talking about here. Most of these new particles are sometimes they're only noticeable or in existence for a few microseconds. And this is, I think, what they were talking about in that one video that I showed you about how they try to measure the spin of electrons. Like they're supposed to either rotate clockwise or counterclockwise. And if they're entangled particles, if this one rotates this way, the other one rotates the other way if they're entangled. Again, I don't really get it. So don't feel bad if you don't. So, anyways, this was my little slide talking about the other way of measuring mass. Are you guys all comfortable with that concept? So rather than kilograms, rearrange E equals mc squared, use a mega electron volt, divide by the speed of light. Keep in mind, like, the speed of light is 3 times 10 to the 8. So you're dividing by 2 of those, right? That makes it really, really small. And the electron volt is already really small as it is, right? So we are talking like the tiniest fraction of mass. So, yeah, physicists were confused too. So, anyways, leptons are really small. Hadrons are a little bit bigger, I guess. So the physicists then realized or reasoned then leptons were maybe as small as it gets. Maybe it's not, but they figured, well, maybe hadrons then can get broken into pieces. So maybe leptons are as small as it gets. Maybe these guys right here, these things here, you cannot break electrons and neutrinos and muons and tauons and all that stuff. Apparently they think maybe you can't break that into pieces. but maybe you can break this stuff into pieces because these guys are relatively large, right? Like these are hundreds and thousands to like 100 or 0.17. Right? So the thought then, oh, quick break here. Anybody want yogurt, muffins, apples, oranges, bananas? No, these guys are really engaged by physics right now. Thank you. How can you eat when we're learning about quarks? Okay, anyways, here's the concept. Maybe the hadrons are made up of smaller things called quarks, and so they suggested that maybe things are made up of fractional charges. So they theorized that maybe there's something called an up quark and a down quark. Okay? The way this would work then is an up quark would have, say, like a positive 2/3 of an elementary charge, which just seems to break all of the rules we've learned so far because Millikan discovered that like an elementary charge, the smallest you could have is 1.6 times 10 to the minus 19. Well, the thought was, well, maybe a proton really isn't one unit. Maybe a proton is made up of like multiple smaller pieces to it. And there's like a 2/3 and a 1/3 piece to it. And so this actually explained a proton, perhaps. What if a proton was made up of two up quarks, which we use a U for, and a down quark, which we use a D for? So you might see this notation. This is something that I have seen them test on. Something like this, UUD. Okay, and they might ask you, what is a UUD? Okay, well, a U, you guys can even see this on your data sheet. A U is an up quark. It's positive 2/3. A second U, also a positive up quark, positive 2/3. What's 2/3 and 2/3? 4/3. Well, that's more than one unit of charge. But what if there was a D in it? A D, a down quark, they think is a negative 1/3 charge. So what if a proton was made up of a positive 2/3, a positive 2/3, and a negative 1/3? Well, 2 and 2 would give you 4, but subtract 1, it would give you 3. This essentially is what they think a proton could be made up of. So a proton is not a fundamental unit. A proton is actually made up of three things, two of them being the same. Two positive pieces and a negative piece that are like in fractional increments. Crazy. Well, now I don't fully know the science behind this, but apparently there's some actual physical evidence that can help prove that this might actually be true. And I found this picture online to kind of illustrate it. From what I understand, physicists then shot electrons really close to a proton. So think gold foil experiment, right? You shoot your electrons, but you're shooting them just at a single proton. And what they discovered is if you shoot them really close to this side of the particle over here, it really deflected. And if you shoot it a little bit further away, it deflected maybe just a little bit. Right? Now, if this thing were a proton should have a positive 1 charge, right? Well, it would make sense that electrons would want to go towards and kind of get sucked in towards the positives because negative comes in towards positive, right? But then they discovered that some of the electrons that went on the other side of the particle, they actually deflected away as well. But hang on a sec, if these electrons were right here, wouldn't they want to go this way as well? Because don't negative things want to kind of get attracted towards the positive? But they discovered that it actually didn't. It actually went away the opposite direction. The thought then being, maybe a proton, which yes has a net charge of 1, is actually made up of a couple of positive 2/3 that could be on this side of the particle, which is why the electron gets sucked in over here. But what if there was the negative 1/3 remaining bit? Well, then this negative and this negative right here would actually want to cause it to repel away. So apparently there is evidence that suggests that a proton is actually not a fundamental unit, but that a proton is made up of two up quarks and a down quark. That makes sense? Strange stuff. This actually helped to explain beta decay. Do you guys remember beta decay? What does beta decay involve? A neutron turns into a proton and electron, which would then indicate that a neutron is also not as small as it gets. Maybe a neutron also has quarks inside of it. So if a proton is made up of some ups and some downs, the theory is maybe a neutron could do this too. So I snagged this out of some book somewhere. This is what a neutron would be, an up and two downs. Because the up would give you positive 2/3, and then the down would give you two negatives, right? So go up by 2/3, go down by a third, go down by a third, you're back to neutral. Does that make sense? So in theory, this explains a neutron. a neutron is also made up of some atomic particles. Now, I'm just going to write them out one more time just to make sure it's visible here. A proton, then, would be an up, and a down, and a neutron would be an up, a down, and a down. What would electrons be made out of? None, because the thought process is that this only applies to the hadrons, which are relatively large, and so electrons aren't made out of this same sort of stuff. Although that logic kind of makes sense, that's not really what they're suggesting. They're suggesting that electrons are something different entirely. So, what's the difference between a proton and a neutron then? Well, this has an up, this has a down. This has an up, this has a down. But a proton has an up here, and a neutron has a down here. That seems to be the only difference, is that the internal structure of these quarks is slightly different. Rather than there being a plus 2/3, a plus 2/3, and a negative 1/3, it's a plus 2/3, a negative 1/3, and a negative 1/3. So really, this plus 2/3 right here has to change itself into a negative 1/3. And that was how they figured they could explain beta decay. Because remember, in beta decay, a neutron turns into a proton plus an electron. That's what happens in beta decay, right? Neutron breaks up into a proton and electron. Well, maybe it's not breaking into pieces so much. Maybe what's happening is this down is somehow turning itself into an up. Well, that's what I kind of have for the math right here. If you have an up, and a down, which is the neutron, and you have an up, and a down, you're missing charge. How do you get from negative 1/3 to 2/3? Well, it means you have to become more positive. Well, you can't all of a sudden just become more positive, right? That would break the law of conservation of charge, right? How much charge is there from a negative 1/3 to a positive 2/3? One full unit of charge. They suggest, well, maybe that one full unit of charge is the electron. So the cost of going from the plus 2/3 down to the minus 1/3 is that it produces an electron out of that somehow. It actually kind of explains beta decay. Right? Protons and neutrons are not actually fundamental particles. They're actually made up of smaller units. So if a proton is an up, and a down, and a neutron is an up, a down, and a down, what's happening here is that this down right here converts itself to an up, and in the process spits out an electron. That's the theory. At least it's a somewhat rational way of explaining it. Again, I don't fully get it. I just memorize information. So here's my summary then. You need to read your textbook. This is the one section here where normally I don't do a lot of work with textbooks. You should read through some of these chapters here. Because here's kind of a snippet I took out of there. This is now known as what's called the Standard Model now. And it was proposed in '78. And basically the idea is they think there are now 12 fundamental particles, which I think would have been on the previous slide I would have shown you there. And there's a whole bunch of leptons and some quarks, and then there's the antiparticles. And like it actually predicted new particles like W's and Z's. And even in the news recently, you may have heard of the Higgs boson particle. They also mentioned this on the Big Bang Theory TV show, if you watch that, where there was a proposal by Higgs. He predicted a new boson particle would eventually be discovered. And it wasn't that recent ago. I think it was like 2-3 years ago that the Large Hadron Collider actually managed to create this Higgs boson particle. And they discovered a particle that he predicted would eventually show up if they, tried hard enough, I guess. So, anyways, read your book. So here's what I want to do last. These last slides here are basically a summary of all the things that you're supposed to have learned. And I just want to kind of tick them off and make sure that you feel like we've talked about this at some point in the last little while, because this section here, it's not about math. It's all about memorization and theory and history. It's a little more like social studies or biology than it is like our previous science courses, because this is not an applied section whatsoever for what you guys need to do. It's more memorize stuff, regurgitate stuff, know the context of stuff. I don't know. To me, that feels like social studies mixed with bio. You're not writing an essay, but fair enough. So here's what you should have learned at some point. Do you know that matter has positive and negative charges. We've talked about that at some point. Who discovered the positive and negative charges? Well, Thomson figured out that bit there, yeah, right? Which I guess kind of goes to the next points. They kind of go together, right? Cathode rays helped develop atomic models, right? Who did the cathode rays? Well, that was J.J. Thomson experiments. What was the contextual significance? He discovered the electron, basically, right? He discovered that an atom is not as small as it gets. You can go smaller than an atom. And that had huge consequences. Explain the significance of Rutherford's experiment. Nucleus is the big one, right? And then in terms of scientists' understanding of relative size of masses of now the nucleus of the atom, really this kind of all goes together though, right? He discovered that not only is all the mass in the center of the nucleus, but I mean if we extrapolate that a little bit further to some of the Bohr models, and you'll notice by the way Bohr's not written on here, but you should know that, is that the Bohr model then starts talking about electrons and different energy levels. Okay, next one here. This actually kind of does lead into Bohr. It doesn't use his words here, but explain qualitatively how emission of EMR by an accelerated charged particles invalidates his model of the electron, of the atom. Because Rutherford would still be working under a classical interpretation of things. You guys remember talking about how if electrons are truly going around a nucleus in a circle, they're accelerating centripetally. What should accelerated things do? Give off EMR, and then it should eventually do that. It doesn't, right? So why is that? Well, that was Bohr's model of the atom, which kind of is the next topic. So it doesn't use his name here, but you should know it, right? Describe that each element has a unique line spectrum. That was the proof that kind of went along with this in terms of saying there were two reasons why this model didn't work. One, classical physics would indicate that electrons should spiral into the nucleus. Two, those line spectrums that we saw when I did the flame test, there was no explanation for this, right? Hence, Bohr's model of the atom is the next thing here. Actually, no, it's not. Before I get to that, you guys are okay with the unique line spectrum concept, though? Because then this next one kind of goes with it as well. Explain the characteristics and conditions necessary to produce line emissions and absorptions. How do you make an emission spectrum? Two ways. What did we do? Flame test or apply a voltage to a gas. Yeah, in a tube. Yeah. Basically, neon lights do that. Okay. How do you get an absorption spectrum? Cold gas, white light. The cold gas will get excited by certain bands of the white light going through it, and it'll absorb them into the electrons, allowing them to kind of jump the energy level. But it has to be a cool gas, right? Because if it's already heated up, those electrons, they don't need to jump anymore, right? So have it be a cold gas, white light. Okay. The next sort of things talk about the Bohr model. It uses a word we haven't talked about before, but the idea is the concept of stationary states, right here, and how the stationary states explain the spectrums, and then the energy level between the states, the idea about how the electron jumps from here to here, and then as it jumps back down, it releases a wavelength of light. So the word they used here are stationary states. Here's state 1, here's state 2. We use the term like N1 and N2. We talked about this, I just didn't use that terminology, but we talked about that. Now this is one of the few times we actually have to calculate something. If I told you that this energy here was 117 joules and that this was 2 joules, could you guys figure out the wavelength? How do you figure out the wavelength if I tell you the energy levels? Subtract them, find the difference in energy, and then use the formula E equals hc over wavelength. You'd have h, you'd have c, and it would give you a wavelength. That tells you what wavelength is emitted. For any of you who've started the assignment, the only math question I think on the entire thing that you would have done is that one with like the bookshelf, stuff like that. You did the bookshelf one, right? Where you have to like calculate the energy as the electrons created the northern lights. It gave you a couple of different wavelengths you had to work with. On that one, it gave you a wavelength and you had to find energy. But they could give you energy and you could find wavelength. Okay, this is one that I had not talked about. There's not a whole lot I need to add to it, though, but I just want to point this one out right here. you're supposed to be able to explain how electron diffraction proved the de Broglie hypothesis. Okay, quick refresh. What did de Broglie say? Yeah, matter can behave as a wave. Now, I didn't specifically talk about this because I talked about this next one right here a lot more. Another way that we proved this is how the two-slit experiment for electrons proved that, like quantum systems, they can be particles or waves. So I just focused on the double-slit experiment. But I need you guys to be aware that electrons can diffract. Okay? Because again, electrons can behave as waves, waves can diffract. So even though I didn't talk about this specifically in class, there was an experiment somewhere in there, probably in your textbook. Someone did an experiment and proved that electrons can not only interfere, but they can also diffract. So, other things you should know how to do. Do you understand the three different kinds of radiation, alpha, beta, and gamma? This is something that you can do a little bit more with. It's not just pure knowledge, but you could actually like ask you, hey, what's the alpha decay for uranium? So, what does alpha decay mean? Drop off an alpha particle, right? So take off 4 off the top number, 2 off the bottom number, and there's your alpha decay. What's beta decay? Neutron into a proton. There's also beta positive decay as well, right? That's where you get the positron instead of the electron. And then gamma radiation is where the nucleus is rearranging itself. It gives off EMR, right, in the form of gamma rays, the highest energy waves we have. That really kind of gets into the next section here. You need to be able to write the nuclear equations for the alpha, beta, and beta positive decays. Okay. And you need to know whether or not to use the neutrino and the antineutrino for these ones right here. Okay. So if they test you on the neutrino, make sure you know which one goes with which one. Okay. Now, here's another thing that you can actually do for calculations. It's one of the only other numerical things we do. You have to know how to do half-life calculations. Right? And that's where it was the formula n equals n0 1/2 to the power of something. Something like that, yeah. So long as you know how to do that in some sort of way, you're good. Now it says that you're supposed to be able to do non-logarithmic ones. But for you guys who I've already shown you how to do logarithms, in theory you could just use logs to solve the problem. But I think the fastest way of doing it is if it says it starts at 100 and ends at 12.5, just keep dividing over and over again. Okay, 100 divided by 2, 50. Divide by 2, 25. Divide by 2, 12.5. Okay, how many times did it divide? 3 half-lives. Just kind of like do it in your head kind of thing. But if you want to use logarithms because you know how, go ahead. You should be able to use laws of conservation of charge and mass to be able to predict a particle emitted by a nucleus. So what they could do is they could give you a question and they'd say you've got x 32 over 20. And I'm going to tell you that it's going to create y 12 over 8, you should be able to tell me what z is. Want to take a stab at it? What's z going to be? Perfect. And then they might ask you, well, what is 20 over 12? And you'd look at your periodic table and you'd say number 12 is magnesium. So the correct answer would be magnesium 20. Does that make sense? Now, this was not a decay. How would you describe this reaction? It's not an alpha decay or a beta decay. What's it known as? Fission. You guys remember fission and fusion? Fusion is where two things combine to each other. Fission is where they break into pieces. This would be a good example of a fission reaction.
Junior high teachers, can you please do your block 1 attendance? Junior high teachers, please finish your block 1 attendance.
Which kind of takes us right into the next concept here. Do you know fission and fusion? Do you know how to figure out the mass defect? One of the other few things that we did math for. I focused on this quite a bit. To find a mass defect, add up all the individual particles of protons and neutrons and whatever it is. Find the mass that's given to you, probably in a chart. Subtract the difference. That change in mass is the mass defect. And that's why you'd be able to quantitatively be able to calculate something. Because that's one of the few times you've either had the word calculate or quantitative there. And then you should be able to find that using the mass energy equivalent. So that's the whole E equals mc squared formula. So far, so good. Okay, and then the last kind of section here. This is what we just talked about today. Can you explain how those particle tracks help people discover the subatomic particles? again, just explain how this occurred. I don't even know how they test you on it. I haven't ever seen a question on this. Some of these things are like not really that testable. Do you get the whole concept of strong nuclear forces and how we would need to have a strong nuclear force to keep a nucleus tied together? Because a nucleus would want to break apart, right? There must be a strong nuclear force, which is why if we want to break things apart, there's so much force keeping a nucleus together. You need a particle accelerator in order to be able to study these sorts of things, right? Again, I don't know how you'd be tested on this. I've never seen a question. So I have seen them test on this, and I'll show you an example of a diploma question maybe in a second here. Can you describe the whole concept of how protons and neutrons are made up of quarks using the up and down quarks? Not electrons. Electrons are not thought to be what was it? Hadrons. Electrons are leptons, and they think that those are as small as it gets. But they think that these hadrons, they can be broken up into the up and down quarks. And then you should also know about, say, your neutrinos and all the antiparticles. And then you should be able to now explain how the two beta decays can be explained using the elementary fermions, which are basically the quarks. I already showed you how the beta decay worked a second ago, right? You've got an up, up, down going to an up, down, down. No, wrong way. An up, down, down going to an up, up, down. The way you explain it is that if you flip a down to an up, it must release an electron. Okay, those are the sorts of things you're supposed to know. Hopefully you feel like I've covered each of them over this section. I find this really frustrating to teach. I don't know how to prep you guys for some of this stuff. There are certain things that I can be like, expect a half-life question. Expect a question talking to you about what scientists did. But like, I don't know how they would test you on this outcome right here. Explain how particle tracks. Like, you can read your textbook and just memorize information. How they ask you to know it, like, I don't know. So, why don't I show you real quick here an old diploma that has a question on it. Since they changed the curriculum, I'm just going to find one here. Let's try this one. This is June 2009. I'm going to give you guys this one at some point. It's probably right at the end of the test. Okay, here, let's start here. So here's a test question. Give you a second to kind of look this over here. There are two possible sequences through an unstable radioactive nucleus of lead-212 can decay into a stable nucleus. They are shown below. The daughter nuclei are labeled 1, 2, 3, and 4. So if you can interpret this diagram here, lead undergoes beta negative decay to 4 and something. Then from there it can undergo alpha decay and beta negative decay. Or from here it can undergo beta negative and alpha decay. And what we have to do is we have to identify these 4 things right here and match which of these 4 slots they'd be in. You guys understand the question? Let's give it a try. What does beta negative decay do? Takes a neutron, turns it into a proton and electron. How does that affect the numbers on this thing right here? What happens to the top number? Stays the same, so it's still a 212. What happens to the bottom number? Up to 1. So we need to go lead up by 1 to 83. So 83 after lead is bismuth. So we need bismuth, but it's still 212. So bismuth 212 would be number 1 then. So a 1 would go here. And that would be in this location here. We'll follow that? Okay, well then it undergoes alpha decay. So the 212 and 83 would lose 4 off the top number. So 212 down by 4 would give you 208. So it's got to be one of these two. But then the bottom number of 83 goes down by 2, which would drop it down to 81, which is thallium. So that means that this one up here, number 2, would be the thallium one. Then it would undergo beta negative decay, which means that it would just go up by 1 atomic number. So it would still be a 208, but if it goes up by 1, that's probably the lead one. So the lead would be in this spot right here. I guess by default, the polonium one must be number 3 then, and I could probably check that by making sure beta negative decay from what I had here goes there. See how they tested that? Very, very clever question design. Here's one that's based on what we just talked about here. The neutron and the proton can be modeled using the quark combinations. So which one of these does the correct ones? Do you want to have the up, down, down, the down, up, up, down? And by the way, I didn't mention these, but if they put a little line over top of it, it just means it's the anti-quark, like the opposite version one of it. So, anyways, what do we need for? We just did this, right? A proton is what, an up, and a down, and a neutron is an up, a down, and a down. So this one was A. That was off a diploma. So that's how they could test that. Oh, that's all I got in there. Okay, anyways, why don't I leave it there? You guys have any questions? I'm sure you have questions, but probably they're not questions I can answer. Okay, we're done the course, guys. Good job. Okay, so you got about half an hour today. Can I ask that you first finish the video assignment? Because I'd like to just mark those real quick and give them back to you. Because honestly, when I'm marking them, I'm just making sure you did them. Really, that's all. And then tomorrow and what are we up to? Tomorrow's Wednesday, Thursday, Friday. I booked laptops so you guys can work on your timelines. Can I have your timelines by May 31st? And then can you guys finish your assignment, the one that's got the 4 questions? Can you finish that by the 29th next week, Monday? So basically take 24, 25, 26, work on stuff. 29, do quiz. 30, one last day to finish stuff. 31, unit test. Sound good? Okay, we'll talk to you guys later.